Now, we are going to basically do the same thing that we just got done doing. Only now they're going to ask us about the type of error that we might have, which we talked about earlier, type 1 and type 2 errors. So I'm just going to remind you since you missed that. So, if I draw my table, if our null value is true or our null value is false. If we reject, almost can read that because it wants to write a little bit farther over than I have it. Now, if we reject the null and the null was really true, then we have what they call a type 1 error. This would actually be the true statement. If we reject it and it was false, that's the true thing to do. If we don't reject, I don't know why they just don't say accept, but they say don't reject the null. If we don't reject the null and it was true, that would be the correct thing to do. Otherwise, we have what's called a type 2 error. So if we reject the null, type 1 error. If we don't reject the null, type 2 error. Problems 4, 5, and 6 talk about that. But we'll talk about them some more. So, problem number 10 says, a union of restaurant and food service workers would like to estimate this year's mean hourly wage for food service workers in the U.S. Last year's mean hourly wage was $8.16. There is reason to believe that this year's value is greater than last year's. The union decides to do a statistical test to see if it can conclude that the mean has increased. The union chooses a random sample of 75 wages this year. Suppose the population of hourly wages of food service workers in the U.S. has a standard deviation of $1.15, and that the union performs its hypothesis test using that 0.01 level of significance. Based on this information, answer the questions below, carry your intermediate computations to 4 decimal places, and round your responses as indicated. So, on all of these ones that we were doing on the previous ones, we had our null and our alternate hypothesis. Here they're going to make you put it together instead of having them separate like on the previous questions we just did. So in this case, we want to see what the question says. It says that it's reason to believe that this year's value is greater than last year's value. So we are checking to see if the mean is, in one of these I'm going to have the greater. You always use the one that does not have the equal sign in the alternate one. The one with the equal sign will always go with the sub-zero one, the null hypothesis. So since I'm doing a greater, the greater's going to go there. Which means this one here, if it's not greater, would be less than or equal to. And we are comparing it to last year's. So last year's number, $8.16. That's going to go in for both of them. So, assuming that the actual value of the mean is $8.57, what is the probability that the union rejects the null hypothesis? Round your response to at least 2 decimal places. Now we're actually going to combine what we did last week with what we did this week into one really big long thing to come up with this one number that's going to go here. So, last week we had a formula that looked something sort of like this. I'm going to take my mean value, and here we had plus or minus, but sometimes we use the plus and sometimes we use the minus, depending on if it's a left-tailed or a right-tailed. Z sub something And then we had our standard deviation times the square root of n. Sort of remember seeing that formula last week? So in this case, we are going to use the greater than, right? The greater than means we're going to use the plus sign and not the minus sign on this problem. So I'm going to put that little note there so you know why I use the plus. So, my mean value here is the $8.16 that we had. Plus, we're going to do Z sub, and that's going to be this level of significance. Right there, 0.01 times the standard deviation. The standard deviation is right here, $1.15 over the square root of n. N is how many people they sampled. They sampled 75 people. We punch that into our Alex calculator. .15, yep, that was our standard deviation over the square root of 75. All right, so you're going to do 816, whoops, 8.16, $8.16, plus, since we're doing a greater, Z sub, so we're using, yep, and then we're going to use 0.01, and then, whoops, then cursor or click up behind there so we can put the parentheses behind that. There we go. Parenthesis, 1.15 divided by the square root of 75. Square root, yep, 75. Click behind there and close the parenthesis. Equals. All right, so we are not done. That's only part of our problem, but I'm going to write that number down. 8.4689, because it says to do at least 4 decimal places. So now this is what we did last week. We're going to combine it with what we did this week. So this week then, we did a formula that sort of looked like this, but they changed it a little bit on us because we have different values. But this is the one we just got done using previously. This value here is going to be your C value when you plug that in. And this value here is going to be that U sub 1 value. So you have to go to your word, or to the question. Okay? So we're going to do 8.4689 minus 8.57 over standard deviation was 1.15 over the square root of n, and n was 75.
So this number we take away 8.57. Okay.
Yep. And then we hit equal, and then when we divided, we put that in parentheses. Oh, and Alex calculator, yeah, it'll go in there nicer than when we use the other calculator. Okay, so hit equals, and then we're going to divide that by 1.15 divided by square root of 75. And hit equals. All right. That number is negative 0.7613, right? We're still not done because now we're to the last step of the problems that we just did. We still have to find the p-value. So, since we're finding this side of a right-tailed test, we're going to do 1 minus the p-value because the p is less than on our calculator of z is less than or equal to that answer, negative 0.7613. If it's a less than, you don't need the 1 minus, but since it's a greater than, we have to do the 1 minus. That's what we did last week. So now you're going to punch that into the Alex calculator.
Okay, so then, do I clear this last number?
Yep, you can clear that last number and do 1 minus. The p of z is less, well, it's probably just less than. I don't think it has the equal to on it. Oh, it does have the equal to. Less than or equal to our negative 0.7613.
Negative
0.7613 equals. And after all of that work, it says round that response to 2 decimal places. 2 decimal places, you get 0.78. So really all of this, just to answer this one question, is doing what we did last week combined with what we did this week and then finding the p-value this week. So it combined all of that stuff into one big super long problem.
Is there a way that we can get the steps? You know what I mean? Like I have all this on here, but like if I go back and look at it later, I'm gonna be confused here on how to get that second part. I mean, we don't have to do it now, but
Right. We'll do a few more anyway. But here we did that first, and then we did this second, and then we did this third. All of that went to find that one number there. But really it's just combining all of what we did up to this point into one big long thing. So, what is the probability that the union rejects the null when in fact it is true? If it asks for what is the probability that it's going to reject the null when it's true, I'm looking at the significance level. So this number and this number should match. Okay? And then now here's where we're talking about the type 1 and type 2 errors. Now here we're talking about a type 2 error. So if we have a type 2 error, we don't reject the null when the null is false. It says, suppose the union decides to perform another statistical test using the same population, the same null and alternate hypotheses, and the same sample size. But for the second test, the union uses a significant of 0.05 instead of 0.01. Assuming that the value of $8.57 stays the same, how does the probability that the union commits a type 2 error in the second test compared to the probability that the union commits a type 2 error in the original test? Well, look at this. If my significance is 0.5 instead of 0.1, you're less likely to commit an error, right? Because I have a bigger room, more room to make more room to make my error. I don't know how I want to say that, but 0.5 would give you more chances to get it right. So in this case, the probability of committing a type 2 error in the second test is going to be less on this one. Because if I had 0.5 compared to 0.1, I have a less chance of making that error. Right? If I only have a 0.01 chance of making the error, then that's more likely I'm going to make an error. If I have a 0.05, I get a bigger room for error, and so it's less likely I'm going to make my error. So, this question here takes all that stuff that we did in Chapter 7 and in Chapter 8, puts it in one great big huge long problem. We'll go ahead and do another one. Then maybe you can get your steps there. So, number 11. A coin-operated coffee machine made by a big corporation was designed to discharge a mean of 6.9 ounces of coffee per cup. If it dispenses more than that on average, the corporation may lose money. If it dispenses less, the customers may complain. Believing that the mean amount of coffee dispensed by the machine is less than 6.9 ounces, Big plans to do a statistical test of the claim that the machine is working as designed. Big gathers a random sample of 150 amounts of coffee dispensed by the machine. Suppose that the population of amounts of coffee dispensed by the machine has a standard deviation of 0.6 ounces, and Big performs its hypothesis test using a 0.01 level of significance. So, first thing we have to do is figure out what the null and the alternate hypothesis is. What they believe is that it dispenses less. So again, since less doesn't have an equal sign, the less is my alternate one. That means my null would be greater than or equal to, right? If it's not less, it's greater than or equal to. The amount that we're comparing it to, 6.9. So for my null hypothesis, I'm going to do greater than or equal to 6.9. For my alternate one, less than 6.9. Which means we're going this way. We're doing to the left side. So, now here's where we have that big long problem that we have to do all those steps on. My first step is using my formula that we had before from last week. We have the mean plus or minus z sub whatever it is, and then the standard deviation over the square root of n. Since this one is going to the left instead of to the right, we're going to use a minus instead of the plus. On the previous one, we were going to the right, we used the plus. I'm looking at number 12. How about I look at this one? So, my mean that I'm comparing it to is the 6.9 minus z sub the significance level is that number there, so 0.01. My standard deviation says it's 0.6 over the square root of n. N, we sampled 150. That's the first thing we're going to do. So, put this into your Alex calculator, find that answer first. I'm just going to write a little note. Plus if it's to the right, minus if it's to the left. And then this we're going to go to 4 decimal places on our intermediate calculations because we got a bunch of steps to do. So once you get that punched into the Alex calculator.
That's 150?
That's 150, yep. That's the number we sampled. We got 150 samples. Yep, that looks right. 6.7.
How many places do you want? 3?
4 decimal places.
6.7860.
Okay, that's our first step. Our second step now is using that formula that looks like the one we did today, but they changed it a little bit because our numbers are different. It looks like this. C minus the mean over the standard deviation and the square root of n. This value here is your C value. This value here is your U sub 1 value. So, we are going to do 6.7860 minus 8, whoops, that's a 6, 6.75 over my standard deviation, 0.6, and the square root of n was 150.
Is that 6.75?
This is this number, 6.7860 minus this number, 6.75. Yep.
Put that in the calculator.
And then we put that into the calculator, exactly. Whoops.
Oh.
Something doesn't sound right there.
Then so
Well, that's
do.
it. Oops. Yeah, undo so I can see what you had typed in. Oh, see what you have typed in? That whole thing should be on top of the fraction, and you've got part of it. Remember we had to hit equal before?
Okay.
So undo a bunch for me. Oh, there we go. Put your 7.5 in. Hit equals first, and then do the bottom of your fraction. So divided by the 0.6 divided by square root of 150. There we go. Okay, so that number is, to 4 decimal places,
0.7355.
0.55.
Yeah.
Okay? She didn't round off, she used the full number on the calculator, so you might have a little bit different number here because if you round it, it will be different. Now, third step. We have to find the p-value. So, if it's less, you just do p of z is less. If we were doing greater, we would do 1 minus p of z is less. The last one we did was a greater. This one we're doing a less. So on this one, we just have to do p of z is less than whatever you got for your answer here. So, I'm going to write it up here. P of z is less than 0.7355. So if I'm doing a less, I can just use the number. If I'm doing a greater, I got to do 1 minus that because I'm doing the opposite. And then I'm going to punch that into the Alex calculator. and round our answer finally to 2 decimal places. So clear that out, do P of Z is less than, yep, or equal to that number. To 2 decimal places, what do you get? 0.77, that's exactly what you should get. Okay? All that work is adding all those steps together as stuff we did in the last couple days. Now, the next part is the easy question. When it asks what the probability is, I'm going to look back at my question for what is my test for the significance level. This number right here. Right? That's how it was on the previous one too. What is the probability? That's what I'm testing. Okay, so last part of this. Suppose that Big decides to perform another test using the same population, the same null and alternate hypotheses, the same level of significance, but this time he's going to sample 125 people instead of 150. If I sample less people, am I going to have a more or less chance of making an error? If I sample fewer people, am I going to have more or less chance of making an error? I'm going to have a bigger chance, right? The fewer people I sample, the bigger the chance I'm going to get an error. So, the probability of committing an error is going to be greater because I sampled less people. All right. Last one on here. Again, these are really long because they're just doing everything that we did. If you can just do this one question right on the test, they wouldn't have to ask you a whole bunch of other things. Number 12 here. A psychologist is studying a smoker's self-image, which she measures using the self-image score from a personality inventory. She would like to examine the mean score for the population of all smokers. Previously published studies have indicated that the mean for the population of all smokers is 80. The standard deviation is 15, but psychologists believe the value for the mean has increased. So if I increased, what math symbol would we use? Greater than, right? The greater than is going to go in for your alternate one because it doesn't have an equal to on there. Greater than 80 is what we're comparing it to, right? 80 was where it was. That means the null is going to be what math symbol? Less than or equal to, right? If it's not greater, it's less than or equal to. The null always has the equal to in it. And of course, it's still going to be compared to that same number. So on this one, since we're doing a greater than, we're doing a right side test. That makes a difference on what we use on our formulas, right? Oh, they switched these around. They asked the easy question first. What is the probability? What is the probability? What number do we use when it asks what is the probability? There's no math to do. We just pick the number out of the word problem. And I think they use the same number on every one of these problems. You use the level of significance, right? So when it asks what's the probability that I'm going to make an error, I'm looking at that level of significance. That's the chance I'm going to make an error. Now we're doing the long part on the second part. They switched it around. So we are going to do the mean. And should we use a plus or a minus when we do our formula?
Plus.
We're going to do a plus because we're going to the right. If it's a minus, we would be going to the left, so we use the plus. Then we had z sub standard deviation over the square root of n, right? So my mean, this number here, 80 plus z sub, and that sub number is your level of significance, so 0.01. My standard deviation says my standard deviation is 15, and my n, I sampled 50 smokers, so square root of 50. Punch all of that in to find our first number, but we have 3 steps to get to the end. Nine what?
934.
3, 4? Okay. Is there a number after the 4 or is it a 0? 9? Because it says to carry it out to 4 decimal places. So that means 4 after the decimal. So 84.9349. Getting that number? Haven't typed it in yet? Still writing? Okay, so we got the 15 divided by, oops, undo that, undo again. Let's do your parentheses first. Now put your 15 divided by square root of 50. And behind there, close your parentheses. So you might just want to put parentheses on here so that you know that you need to put those in there, right? All right, that's the first step. Our second step, we did C minus the mean from the problem over the standard deviation and the square root of n again. This value here is the one that is going in for the C. This value here goes in for the mean sub 1. So 84.9349 minus 86 over my standard deviation of 15 and the square root of 50.
2.1201? No?
Should get a negative number. Clear that out or undo that. Oh, yeah, we got a whole more. Okay, so we have the 84.932. Okay, we're going to minus the 86. Hit equals. Then divide that by the 15 divided by the square root of 50. Equals. Okay, maybe the decimal wasn't in there. Clear that out. Let's just start all over. Okay, 84.9349. Maybe you didn't have a point. 9349 minus 86 equals, or enter, yep. There we go. Divide that by 15 divided by the square root of 50. Equals. That looks better. So, we come up with negative 0.502, right? So we are going to do P of Z is less than or equal to negative 0.502. Draw my arrow.
I'm gonna do that too.
Okay, so clear that out. Do P of Z is less than or equal to negative 0.502. Equals. And this we are rounding off to 2 decimal places. To 2 decimal places we get
0.31.
0.31. Now on this one, even though we were testing to the right, because this was negative, it was doing to the left, and the numbers should end up matching like when we did the 2-tailed test. That's why we didn't have to do the 1 minus on that one because of the negative. Now, the next one is weird. Says, suppose that the psychologist decides to perform another statistical test using the same population, the same null and alternate hypotheses, and the same level of significance. But for the second test, the psychologist chooses a random sample size of 150 instead of a random sample size of 50. Assuming that the actual value of your mean is 86, how does the power of the second test compare to the power of the original test? The power is like the p-value. So when they ask for how the power compares instead of the chances, it ends up kind of being the opposite of what you normally think your answer should be. My percent is going to be lower or higher depending on if I am going to have more or less chance. So when I think about this, if I think about, well, I sampled more people, I would think that, oh, since I sampled more people, I have less chance of making an error. That means your power, your percentage, is going to be a greater value. And so the power for the second one is going to be bigger than the power of the first one. So if you have less chance of making an error, the power or the percentage is higher. It'll be the opposite of kind of what we thought of when we did the other ones. So if I have more chance of making an error, then my power or my percentage is less, and vice versa. Alrighty. That is the end of that one.